Let's dive right into a classic EPC engineering mystery that trips up, well, almost every young piping engineer. If you've ever spent time in process plant design, you know exactly what I'm talking about. That massive, sometimes frustrating gap between textbook theory and practical on-the-job engineering judgment. Today, we're going to bridge that gap. In this explainer, we are going to completely decode what pipe schedules actually are, why they exist, and how seasoned engineers really use them in the field. Picture this. You've got a fresh engineer, let's just call him Arjun. It's late at night, his dual monitors are glowing, he's got a PNID on the left, a piping isometric on the right. Out of nowhere, he spots this simple 6-word comment from his lead engineer pinned to a single line: change this line from shell 40 to shell 80. That's it. There's no calculation attached, no explanation, just a blunt instruction. Now, to a fresh engineer, a comment that looks that simple feels like an absolute trap, right? So, to actually solve this mystery, we have to start asking the right questions. Namely, why was Schedule 80 selected instead of Schedule 40? What actually drove that specific decision? The reason Arjun is stuck here is that most engineering colleges completely skip over the foundational philosophy of what a pipe schedule represents in the real world. So let's reverse engineer the actual engineering judgment that led to those 6 little words. Okay, first major paradigm shift. Ask a rookie what NPS 4 means, and they will almost always tell you, oh, it's a 4-inch pipe. But if you take a caliper out to an actual NPS 4 pipe in the field, you're going to find that the outer diameter isn't 4 inches at all. It's exactly 114.3 millimeters. Nominal pipe size, or NPS, is literally just a historical label. It's not a literal measurement. For most of your common pipe sizes, that outer diameter stays entirely constant no matter what schedule you end up choosing. Well, if the outside stays exactly the same, then what exactly is a schedule? Honestly, a pipe schedule is just a standardized way of expressing wall thickness for a given pipe size. Think of it like standard clothing sizes: small, medium, large. They give you these predefined buckets to choose from. The industry created standard schedules like 10, 40, and 80 so engineers all over the globe could speak the exact same language. It's kind of like a donut. 2 donuts can have the exact same outer size, but the thicker the dough, the smaller the hole on the inside. And that donut analogy perfectly illustrates what happens physically. As that schedule number goes up, the wall thickness increases. Because the outer diameter is permanently locked in place, that extra thickness has nowhere to go but inward, eating into the inner bore of the pipe. This thicker wall is what provides the necessary strength to carry higher internal fluid pressure. Now, this standardization is absolutely brilliant. It means projects can move fast without reinventing custom pipe walls for every single line in a plant. But it's also exactly where the biggest trap lies. Here is the crucial point, and honestly, this causes massive design errors. Schedule is not a pressure rating. Fresh engineers constantly make this mistake. They assume that a higher schedule automatically equates to a specific, guaranteed higher pressure rating, kind of like a flange pressure class. But schedule, all by itself, does not dictate your maximum pressure. It literally only tells you the physical thickness of the steel. That's it. So to figure out what a pipe can actually handle, we have to look at the true factors of pressure carrying capacity. You need the internal design pressure, the design temperature, because, materials weaken as they get hotter, the pipe diameter, and the allowable stress of the specific material you're using. 2 pipes can both be standard Schedule 80, but if one is carbon steel and the other is stainless, their actual pressure capacities are totally different. The material behind the thickness is what matters. Schedule is the outcome of a calculation, not your starting point. The real engineering process begins right here, by calculating the required thickness. Every seasoned piping engineer works backward. They don't just sit down and randomly pick Schedule 40 or 80 out of a hat. They start by calculating a physical, non-negotiable number for the required thickness based on those exact variables we just talked about: pressure, temperature, diameter, and stress. That formula spits out the precise millimeter thickness that pipe needs just to survive its service environment. But, of course, there's a catch. Even if you calculate the absolutely perfect required thickness for day 1 of operations, it's not enough. You have to step back and ask, what happens to these pipes over a 20 or 30-year design life? We have to account for the invisible thief of piping systems. Because internal fluids don't just sit there passively, they interact with the steel every single day. We counter that invisible thief with the corrosion allowance. This is extra deliberate thickness that you add right on top of your calculated required thickness.
Think of it like a savings account cushion. It gets slowly, gradually withdrawn over years of service. The fluid might corrode or erode the inside of the pipe over the decades, but because you provided this sacrificial buffer up front, the pipe loses thickness without ever compromising the structural integrity it needs to actually hold the pressure.
Now, this leads us to a really fascinating paradox. If wall thickness is primarily driven by pressure, temperature, and corrosion, you might be wondering, why not just use paper-thin pipes for low-pressure water lines? I mean, on paper, a low-pressure utility line might only need a fraction of a millimeter of steel to contain the water safely, right? But if you walk onto literally any process plant in the world, you are not going to see paper-thin pipes anywhere. The answer to that is just practical EPC reality. Experienced engineers know that pipes have to survive the physical, chaotic environment of a construction site. A pipe with a paper-thin wall would dent or sag the literal second an operator leaned a ladder against it, or a rigger dropped a wrench on it. So Schedule 40 is frequently used as a practical, robust structural baseline. In these cases, the schedule isn't protecting against internal fluid pressure at all. It is entirely there to protect against human error and gravity. Which brings us right back to our mystery with Arjun. Why did his lead tell him to change that specific line to Schedule 80? Well, instead of just guessing, Arjun actually goes back to the process data sheets. And what does he find? He discovers that a quiet process revision had bumped up the line's operating temperature and pressure. When he recalculates everything, his new required thickness, plus his corrosion allowance, suddenly exceeds the physical thickness that Schedule 40 could provide. Schedule 80 was simply the next standard bucket available that safely covered that new mathematical reality. And this beautifully illustrates the true logical workflow of how an experienced EPC engineer operates. First, you gather your actual design conditions. Then, you confirm the material spec. Once you have that locked in, you calculate the required thickness. After that, you add your corrosion allowance. And then, finally, you select the standard schedule. Notice how picking the schedule is the absolute final destination of this entire workflow? It is never, ever the first step. As you level up in your engineering career, you're going to start to recognize these patterns naturally. You'll stop making beginner mistakes, like assuming a higher schedule always means a stronger pipe, regardless of the material. You'll learn the industry thumb rules, like knowing SHUD 40 is a great utility baseline. But you always have to remember, these patterns just help you recognize what looks right. They can never, ever replace the foundational math. All right, to wrap up this explainer, I want to leave you with this core philosophy. Schedule is not the starting point. Required thickness is. That lead's comment to Arjun wasn't some arbitrary guess. It was the compressed output of an entire chain of engineering judgment covering pressure, material, corrosion, and physical reality. So the next time you're reviewing a drawing, ask yourself, are you just picking a schedule out of a catalog, or are you actually engineering the pipe?